All right, okay. So let me introduce Dr. Alan Coley from the Department of Mathematics and Statistics of Dalhousie. Dalhousie University of Canada. So he's going to open this COMCA, and he's going to talk about open problems in mathematical physics.
Thank you very much. I just wanted to make two very brief comments. Firstly, to say hello to everybody. Secondly, of course, my Zoom name is Albert, so this is really Alan. I had to use a different name for legal reasons. And I'm from the University of Northern Chile in Canada. So I've sent a video to be played, partly because it just to avoid any technical difficulties. But what I'm going to do is I'm going to be online during the talk to answer any questions. If you have any questions, send them to chat and I will answer the questions in chat. If there's anybody that cannot speak English and wants to ask a question in Spanish, if they ask it in chat and somebody translates it, I can answer it at the end of the hour. So anyway, I just wanted to say hello. Thank you very much.
Bueno, ahora la presentación, ¿no? Yeah.
Hello, my name is Alan Coley, and I'm from the Department of Mathematics at Dalhousie University, and I'm going to give a talk on open problems in mathematical physics. A couple of comments about the format. I've used red outliner to remind me basically what I want to say in the talk, and I'm using blue effectively for definitions and for details and exact statements of problems, although here that doesn't quite fit the definition. So the idea is to present a list of open problems in mathematical physics. This talk is taken from this reference here, where everything is given in more detail. In particular, I'm going to refer to several famous lists, and all of the questions in these famous lists are displayed in the paper. And there are some sections in the talk where I go into very little detail, and I may have an asterisk here to indicate that the details are found in the paper. There are going to be 6 sections. The first section is an introduction, which I'll do in this video. The second is a definition of what I mean by mathematical physics and the types of problems that would be included in such a list. Sections 3, 4 and 5 are open problems in general relativity, the quantum realm and cosmology. And if time permits, the last section is actually a list of all of the 42 open problems that I've described. So to begin with, let me start with the introduction. This is really a little bit of a historical context. I want to sort of describe different areas of mathematics and why we divide it into pure and applied and what it actually means. Try to give you a sense of the cultural role of questions in mathematics. It has a unique role in mathematics that doesn't perhaps occur in other topics. And maybe talk about one or two of the very famous problems that have captured mathematicians' imaginations. So there are essentially 2 branches of mathematics, pure and applied. Of course, this is an artificial barrier, and the actual mathematics that mathematicians do is exactly the same. It's possibly just the motivation between pure and applied mathematics is slightly different. You might say that pure mathematics is concerned with mathematics for its own sake, proving theorems, and it's assessed to be a good problem. A pure mathematics problem is assessed to be a good problem if it leads to new fields in mathematics. Applied mathematics is also concerned with establishing facts about the real world. So the problems themselves might be motivated from science, and in particular physics. As I said just a moment ago, noted problems in mathematics have always been important and a part of the mathematical culture. in olden times, it was a test of one's acumen, and was a recreational endeavour. And indeed, the central figures in mathematics have always played an important role, and so what they think to be the most important problems have always been associated with additional importance. Now, I have two examples of problems that have occurred in the past that perhaps give you a sense of this cultural heritage. The first one is problems in solving cubic equations, which is the problem that's outlined here. Let me just go to the second problem, just to give you an idea of the type of historical context. So, famous mathematician John Bernoulli published a problem, and the problem was this. So this is in the 17th century. Find the curve connecting 2 points. They're at different heights and not on the same vertical line, such that a body acted upon by gravity only will forward the shortest distance. So this is called the brachistochrome problem. Now, I'm not sure whether this is true, but the folklore says that Leibniz and Bernoulli were confident that you could only solve this problem using calculus. And at the time, the only people that were known to understand calculus was Leibniz and his group, and Isaac Newton. Although at that time there wasn't a communication between the two groups, and so in a sense Leibniz didn't really know where Newton was. So the idea is, or at least the folklore is that this problem was posed in part to find out what Newton knew. Within 1 day of receiving the challenge, Newton sent in his solution. When Bernoulli announced the winners of the contest, he named Leibniz and L'Hopital as the winners, and an anonymous winner, which he believed was Newton. And he said, or the quote is, Bernoulli recognised the anonymous winner in public with the phrase, "We know the lion by his claw." So perhaps the most famous list of problems is the list of problems published by the German mathematician David Hilbert. All of the problems at the time that he published the problems were unsolved. Several of the problems have been extremely influential in mathematics, in the development of mathematics. Since that time, there have been several people and institutions that have announced new lists of problems, but I think it's fair to say they haven't had quite the same influence as the original questions by Hilbert, although I will mention a couple of these lists in a moment. So Hilbert's 23 problems were published in 1900 and ranged over a number of topics that were contemporary at the time. Some of these problems were stated precisely enough to enable an answer, others were not. In fact, some of them were formulated so imprecisely that I think nowadays one wouldn't even include them as legitimate problems in mathematics. At the time of publication, all of the problems were unsolved. Some of them were very influential. These numbers, H11 and H16, are the numbers of the actual problems in the list. The full list is in that paper reference that I gave, and the unsolved problems I'll actually indicate in a moment. And some of the problems have actually given rise to solutions that have actually garnered a lot of attention. One of the most noteworthy problems is the so-called Riemann hypothesis. This asserts that all non-trivial zeros of the analytic continuation of the Riemann zeta function have a real part of a half. So the Riemann zeta function is a function that appears in analysis, and this problem concerns the location of the real parts of the zeros. And as it says there, it's still an important problem and would have an important role to play now if it were to be solved. This is indeed a problem in mathematics. I don't think anybody would claim that this is a problem in mathematical physics. However, these lines get blurred because even this famous hypothesis, which is a problem in pure mathematics, has a potential application in physics, in the sense that the energy eigenvalues of certain distributions of random matrices, which are important in nuclear physics, are given by solutions of the Riemann zeta function. And there are in fact experiments that look for these energy eigenvalues, which actually pictorially give you the zeros of the Riemann function. So you can actually see the Riemann eigenfunctions in experimental setups. So here are the 4 unsolved problems of Hilbert. The first is the mathematical treatment of the axioms of physics. The second is the Riemann hypothesis. And there are 2, so these are the problems that are unsolved today. And H12 and H16 are problems in pure mathematics. Most of the original problems were in pure mathematics. Only a few of them would be regarded as problems in applied mathematics. But H6 is an interesting one. It's basically to put certain areas of physics on a more formal mathematical level. It's very vague, and as we'll see with problems I describe in a moment, the problems that probably suit themselves to or could be called problems in theoretical physics, mathematical physics, are problems where you can actually describe systems by differential equations, and you can pose a well-posed mathematical problem about the behavior of the differential equations. Even though it was vague, Hilbert did try to direct attention towards 1 or 2 particular areas of physics, and namely, he looked at the axiomatic treatment of probability in statistical mechanics, and limiting processes to the laws, using limiting process, well-defined mathematical limiting processes when looking at the laws of motion of continuous media. And as it says there, both of these problems to some extent have some, there have been progress, but the original problem was too vague and too vast to perhaps hope to answer it in totality. Sometime later, namely a century later, Vladimir Arnold suggested there should be an update on the questions, and he basically inspired Stephen Smale to produce an updated list. These are called Smale's problems. Of course, 2 of the problems are Hilbert's original problems, in the sense that the unsolved problems of Hilbert, not taking into consideration the mathematical physics axioms, are still unsolved problems, and so it's still regarded as important problems. Another problem was the Poincare conjecture. The Poincare conjecture asserts that in 3 dimensions, a sphere is characterized by the fact that it's the only closed and simply connected surface. I said that incorrectly, but in 3 dimensions, it's the only closed and simply connected surface is a sphere. This was actually solved by the Russian Perlman in 2003 using a relatively new branch of mathematics called Ricci-Flows. And this is an area of mathematics that now is very topical. Here are the list of unsolved problems. P equals MP, I'll talk about that in a second. S4, you can see the designation S is Smale's list, problem 5 and so on. This problem here, S8, is basically putting financial mathematics on a well-posed, rigorous mathematical basis. Problem in linear program. S10 is problem in pure mathematics. So is 16. 18 is rather more philosophical. And you'll see that S15, do the Navier-Stokes equations of fluid mechanics have a unique smooth solution. So here's the applied mathematics problem, mathematical physics, and one of the realizations of the original mathematical physics problem that Hilbert posed. Just a quick problem, the problem PMP, does P equals MP. This has to do with the fact that some problems can be solved by computer by using an algorithm, and the algorithm may be very slow, take a long time, and maybe because of its time frame, the problem becomes practically unsolvable, or whether there's an algorithm that can find the solution quickly, meaning in polynomial time. That's what the P stands for. So the question is, are all problems in MP, all problems for which there's an algorithm, can they always be solved by for want of a better phrase, a simple algorithm? And the most famous version of this is perhaps the travelling salesman problem. Given a list of cities and the distance between each pair of cities, what's the shortest possible route that visits each city exactly once and returns to the original city? And to date, it has not been proven that this particular problem can be solved in polynomial time. And I think most mathematicians and computer scientists, of course this is of interest to computer scientists as well, believe that it's not true. And this problem is also on another list that I'll talk about in a moment. Financial math could be regarded as an area of mathematical physics, and again it's looking at the well-posedness of the differential equations that represent the models. Navier-Stokes equations are the equations that govern the motion of fluids and gases. And there are well-defined differential equations that represent the models that one is studying. So to look at, to analyze questions in terms of the existence of solutions, smoothness of solutions, which is basic analysis studying the behavior of the differential equations, is, I would propose, a true problem in mathematical physics, and is one of the types of problems that I think Hilbert had in mind when he was talking about formulating or axiomizing theoretical physics. Just to give you an idea, because of course when talking about mathematical physics there are various areas that one can consider, and fluid mechanics is probably the most important. So just a comment about the types of questions that arise. Firstly, solutions of these equations. Euler's equations are a set of equations describing some particular systems in applied mathematics. These solutions develop singularities, so how to study these solutions. Finding proofs for the existence of singularities is hard. You can get shock waves occurring. How do you treat shock waves? Many solutions of physical interest are said to be weak. So can we prove theorems on weak solutions? Where I won't say what I mean by weak, but solutions that have certain types of properties in an integral sense. And again, there's been some progress in looking at these types of problems, but no general theory has been presented. Also, around the turn of the century, the millennium, the Clay Institute of Mathematics in 2000 presented seven important problems in mathematics, and also offered a prize of $1 million US. Of the questions, the 7 questions that were posed, one has been solved, namely the aforementioned Poincare conjecture, and the other 6 include the Riemann hypothesis, M versus MP, and the existence of smoothness of Navier-Stokes equations, and 3 more. M1, pure mathematics, M3, pure mathematics. M2 is a similar problem to the problem in fluid mechanics, in the sense that there's a theory called Yang-Mills theory, and there's a quantum version of this theory which is well posed and written down in terms of differential equations, and so there will be mathematical questions about the system of equations and of the physical implications. So this is basically looking at something like Yang-Mills theory or Maxwell's theory of electromagnetism, and asking questions about the well-posedness of the differential equations. Here's a little comment about what the mass gap problem is itself, but basically it's the field of studying the differential equations in Einstein, in Yang-Mills or in Maxwell theory. I'll stop there for the time being. In this second section, I'd like to try to be a little bit more precise about what I mean by mathematical physics and what types of problems can be regarded as problems in mathematical physics. Clearly not all mathematical problems in pure mathematics, are of interest to a physicist. So intrinsically, a problem in mathematical physics is not a problem in pure mathematics. Nor is it true that all problems in physics, in theoretical physics, are of a mathematical character. There are many problems in physics, and if you go to a reference to open problems in physics, you'll get a list more or less similar to the one I'm going to give in just a moment. But if it's theoretical physics and it's on the vanguard of new research, often the problems are not particularly well formulated, and so they don't give rise to rigorous mathematical questions. The exceptions might be topics like general relativity and quantum gravity, where there is a mathematical formulation that can be studied. One of my favourite quotes in mathematics, physics, is the quote by Werner von Braun, the rocket scientist, who said, "Basic research is what I'm doing when I don't know what I'm doing." So, most important unsolved problems in theoretical physics. And the problems tend to be theoretical physics, they tend to be problems in the small and in the large, where there's a lack of observations and experiments, and so theoretical results play a more important role. This is a typical list. Problem of quantum gravity, formulating a theory that unifies quantum mechanics and GR. Foundational problems, interpretational problems in quantum mechanics. Particle physics, tuning problem, that's kind of like the philosophy behind quantum mechanics, problems concerning the philosophy behind, and problems of in cosmology, which is based on general relativity, which is a well-formulated set of differential equations. So, in general, problems in mathematical physics will not include problems where the basic underlying physics is not understood. The theory has to mature sufficiently that a precise, rigorous mathematical problem can be posed. So, as I said a little bit earlier, those theories, Navier-Stokes, Maxwell equations, Yang-Mills equations, general relativity, where there's a well-formulated set of differential equations, you can start asking rigorous problems. Rather than being too semantic and giving a definition, it's illustrative to look at what types of problems people are interested in, and I think this is nicely illustrated by a set of problems by Barry Simon, which I'll talk about in just a moment. There are a number of problems, and various people have put forward problems in various disciplines, which would go under the banner of problems in mathematical physics. There's a few commented there. There's a few lists that are referenced. Let me just mention one or two. The DARPA mathematical challenges were proposed, which are very heavy in applied mathematics and theoretical physics. And they consist of problems in open problems in classical fluid dynamics, such as the Navier-Stokes equation, their use in understanding shock waves, turbulence, and solitons. All of these can give rise to rigorous mathematical questions, and also problems in looking at complex fluids, things like analysing listed liquid crystals, and the so-called Langlands program. There are a number of other fields for which you might claim there might be open problems. Let's call them more speculative topics. Work in the brain, stochastic problems, problems in theoretical biology, biological quantum theory, the mathematics of quantum computing, of which we have a very strong group here at Dalhousie. So there's a number of problems that, shall we say, might be associated with very modern areas of physics, although I'm sure my colleagues would claim that there are some very precise mathematical questions in quantum computing. There are also even more speculative questions to do with studying, let's see, consciousness, the brain, what else have we got? Some philosophical aspects of cosmology, problems in ethics. Probably most of these problems would not fall under the umbrella of problems in mathematical physics, but I've referenced an article here by Allen and Lidstrom, which talks about some of these problems in theoretical physics in more modern contexts. In the same way that certain characters in pure mathematics have influenced the field, there are a few people that I might mention that are have influenced mathematical physics. Perhaps first and foremost would be Ed Witten at Princeton. He's the only physicist to ever be awarded the Fields Medal, which is the highest honour that you can be awarded in mathematics. As you can see, it's like the Mathematics Nobel Prize. Mathematicians that greatly influenced physics would be Roger Penrose, Michael Atiyah, Stephen Hawking. These are mathematicians, although their work may be known in physics, particularly Stephen Hawking. Stephen Hawking in his later life probably focused more on physics than he did on mathematics, but he was a mathematician by training, and his original research was in mathematics. These people have influenced physics greatly. Atiyah's student, Simon Donaldson, has been very influential more recently, and he has basically begun several fields of mathematics which have applications to physics. Here I've just mentioned here the application of gauge theory. And famous mathematicians like Yao and Schoen, basically analysts, differential geometers, who have become interested in problems in general relativity and mathematical physics in general. Just a little note here. One area of quantum gravity that's particularly popular is string theory, and it's strange that most string theorists are now in mathematics departments and in physics departments. So Simon's problems. Barry Simon's problems, a set of open problems, 15 problems. Who was a well-known mathematical physicists. The questions are varied and will be in topics like fluid mechanics and stochastic equations, stochastic differential equations. Just mentioning one or two. These two problems here are in fluid dynamics. There's one question in ergodic theory. In statistical mechanics, it's observed that systems of bulk systems quite often rapidly approach an equilibrium state. And it was originally believed that this could be proven that the classical dynamics in general tend to an ergodic state. However, there's a famous theorem, the KAM theorem, in dynamical systems about the persistence of something called quasi-periodic motions, which implies that many systems are not ergodic. And then there's some problems in renormalization theory. Renormalization theory was introduced by these people here, particularly Wilson, which describes critical phenomena, which can be used to describe something called universality in physics. And this was this topic was attempted to put this topic on a more mathematically rigorous framework. Various people have put forward problems in general relativity, particularly Yao, which we just mentioned. Penrose has put forward a series of questions, and a little later, somebody who's perhaps not as well known in the mathematics community is Bartnik. These questions here were kind of more sub-problems which needed to be solved to pose the more grandiose open problems that we would now recognise. And Bartnik actually stated these theorems in a more general sense. I'm not going to say anything more there. There are various problems, and of course in general relativity, because the equations are written down in terms of differential equations, well-posed differential equations, lots of problems can be posed in a rigorous fashion. Okay, I'll stop there. So in this third section I'm going to discuss problems in general relativity. You'll notice a little star there, and this section has a lot more technical details, and so here I'm just going to try to give a little bit of a flavour. Let me just put it into some context. In general relativity, the background mathematical structure is a differentiable manifold, four-dimensional differentiable manifold with a Lorentz structure, which gives you the causal structure of the manifold. And the Einstein field equations constitute a set of differential equations that govern the fields, the metric, and any matter fields, and they constitute a hyperbolic system of quasi-linear partial differential equations. Of particular interest, and this is normally done in the vacuum case when there's no matter, is the so-called Cauchy problem and setting up a well-posed initial data problem. Within this context, once you've set it up as a rigorous mathematical problem, you can actually pose and attempt to answer various types of mathematical questions. Now, as I said, I'm not going to try to go into too much detail. There are a number of problems that arise. Some of them are differential geometry problems, in the sense that the Einstein field equations are generally covariant, independent of coordinate choices, which raises some issues. There are problems trying to prove the existence of solutions, existence and uniqueness, and there are problems trying to generalize the theorems to situations which have lower differentiability, which would be of interest in physics. There are physical problems that would not necessarily be smooth. The geometry would be necessarily smooth. Perhaps the most famous theorem in GR, which I'll just state as a theorem, so this is not an open problem, although many open problems still arise from this. So the singularity theorem is perhaps the most important theorem, possibly even within mathematical physics itself. Penrose was the first person to talk about singularity theorems and prove a theorem. Hawking later applied the mathematical results of Penrose to situations in cosmology, and the book by Hawking and Penrose perhaps summarizes the status of the singularity theorems best. We can see here a relatively technical definition, statement of the theorem, but basically it says that generically solutions of Einstein's equations, namely spacetimes that arise as solutions of Einstein's equations, have singularities. This theorem has been proven since in various cases, which has led to many, many more open problems. But let me just move on to perhaps the one that's of most interest now, the so-called cosmic censorship hypothesis. So the general theorem of Hawking and Penrose implies the existence of a singularity, but doesn't say anything about its nature. The first solution to be found that had a singularity was a Schwarzschild solution, but in the case of the Schwarzschild solution, there exists an event horizon which shields the outside of the horizon, namely us, from the singularity within. So it's not a particularly damaging singularity. So the question is in general, are the singularities of the type of Schwarzschild and therefore relatively meek, or are they more dangerous? And in order to study this, Penrose proposed the so-called cosmic censorship hypothesis. Whoops, which basically asks the question, is the Schwarzschild situation where an event horizon develops the generic situation, or is it not the generic situation? How serious are these singularities going to be? Now, of course, this question has to be framed in a rigorous mathematical fashion. Let me see, where am I? We need to have a particularly well formulated expression of this censorship to be able to answer a question, and that's one of the problems. There is no well-defined formulation of this particular hypothesis. So people try to prove subcases, if you will. One of the problems that arises is that there are known solutions of general relativity in which there are no singularities, or in which there is a singularity but it's not enveloped by a horizon, event horizon. So the problem is you can't prove a result that says there are no singularities that are not shielded by an horizon, because there are known examples. So we have to prove a theorem that says in general there are no destructive examples, which makes the conjecture harder to prove. There are actually two different versions of this conjecture, related to each other but distinct. The first one prove that for a generic initial data, using the evolution equations of GR to propagate the solution, there cannot develop any naked singularities. Now, this is a well-posed problem, but still not solved, although it's been studied in some particular subcases. You can see here I've stated the problem: prove the weak cosmic censorship. The second one's more technical, and here is it stated, but both aspects are to do with the fact that general singularities in general relativity that develop from well-posed data have event horizons. Now, there are a number of other problems that are of interest, which I'll just skip through here. These are conjectures that would, if solved, would give us some opportunities or lead to possible roads for proving the cosmic censorship hypothesis. Another class of problems in GR, mathematical problems, is talking about stability of solutions. Famous solutions like the Schwarzschild black hole or the Kerr black hole, which is a rotating black hole solution. Are these solutions stable? Are they stable to certain types of perturbations? There's also the question of uniqueness. Given a certain situation, is the only solution a black hole? And is the solution, if it is a black hole, one of the classical black hole solutions like Schwarzschild or Kerr? So stability and uniqueness, of course, within the theory of differential equations, since we have a well-posed problem, these are questions that we can ask. Unfortunately, they're very difficult to answer. There is some progress in the case of Schwarzschild, but the Kerr-Newman, the Newman is the generalization of the Kerr solution. The Kerr-Newman has not yet been proven to be stable, and this is an area of intense research currently being undertaken within both general relativity and analysis in general. There are also problems that have a more cosmological origin, which I'll talk about in another section. Various other problems, the role of scalar curvature invariance. This is something that I'm interested in myself, trying to describe the geometry in terms of scalar invariance as opposed to tensors. And I'm going to stop there. So let me next turn to open problems in the quantum realm. Earlier I had a list of problems that physicists would consider to be open problems in theoretical physics. Most of these problems, and those that list that I provided earlier, I do actually go into a little bit of detail about what those various problems are. But ultimately the most important question is there a theory, a unified theory that unites both general relativity and quantum mechanics into a single unified theory of quantum gravity? Now, even this problem, the other problems mostly do not give rise to problems in open problems in mathematical physics, and this problem in itself, the problem of quantum gravity, doesn't necessarily give rise to a mathematical problem, but it does give rise to a number of questions which probably do fall under the umbrella of open problems in mathematical physics. I'm just going to talk about one or two. There is a space-time, a classical space-time, like a solution of GR, which in 4 dimensions is a unique maximally symmetric Lorentz manifold with a constant negative curvature, scalar curvature. Namely, it has a negative cosmological constant, and it's the only matter field in the model. These space-times arise and are of interest from many aspects of quantum gravity. I've mentioned one or two here, but these problems, these spacetimes, crop up in a number of very interesting situations. Now, anti-de Sitter space is just a classical solution of general relativity, so we can talk about its stability in very much the same sense that we can talk about stability of other solutions of GR. The difference here being is this particular space-time is of particular interest in quantum gravity. Certainly within the area where it's been motivated, we would hope that this space-time was stable. So there's motivation for studying these space-times. Now there are 3 maximally symmetric space-times. There's the Minkowski space, vacuum, the case lambda is equal to 0, positive lambda, which is called de Sitter space, and both Minkowski and de Sitter spaces have been proven to be stable, at least linearly stable, a long time ago. It turns out that the ADS spacetime is a harder nut to crack, but it's turned out recently there's some evidence that it's not stable. It's actually been shown by a combination of some analytical results and numerical results that ADS appears to be unstable to small perturbations. Now the problem is, of course, is that these examples that show it's unstable don't prove stable unstable in general situations. And of course the examples are very special because the problem's difficult. For example, it's spherically symmetric systems have been studied and found to be unstable. So the aim to prove stability in a more general context is very challenging. So the ultimate goal is to prove or disprove the stability of anti-de Sitter, or at least in the first instance to determine whether it's non-linearly unstable to general nonlinear perturbations. In particular, in the case that people have studied, these special cases, there is, in which they do find an instability, there's a very interesting phenomena that occurs describing how the instabilities occur. There's a mechanism which is reminiscent of turbulence that causes the instabilities to develop, and certainly not the whole space is unstable, but certain regions are. So the question is there some evidence for very simple some situations that the ADS spacetime is unstable, but certainly no general results. So the problem would be to prove some general results about stability, and this is a very, very hot topic in mathematical analysis. In many theories of many ideas in quantum gravity, the universe is supposed to be higher dimensions. So in general relativity, the universe is supposedly 4 dimensions. Within quantum gravity, we may be looking at high dimensional space-time, which means that it may be of interest to revisit old questions in 4 dimensions to higher dimensions. For example, the uniqueness and stability of higher dimensional black holes is of current interest, generalizing any theorems that we had in 4D to higher dimensions. This is also a topical subject. I won't say anything about that. Another problem that arises is the question of quantum resolution of quantum singularities. Now, the Hawking-Penrose theorem says that generically singularities arise in general relativity. Now, if we go to a full quantum theory of gravity, do those singularities persist, or are they resolved? Now, there are 2 popular approaches to quantum gravity. One is something called loop quantum gravity, which is kind of like an approach based on 4D general relativity and geometry, and string theory, which is perhaps more based on a particle physics approach. So the question of black hole singularity resolution and cosmological singularity resolution has been addressed. There are claims, at least for very simple spacetimes, i.e. They have symmetries and perhaps there's no inhomogeneities, that the singularity is resolved. So in this case, these theorems need to be generalized to more physical situations. On the other hand, in string theory, although some singularities are resolved, not all of them are. So the question is a little less clear in string theory. So this is an area of ongoing research. Can you resolve singularities within quantum gravity? This just mentions that the way that, for example, the singularity is resolved in cosmological models for loop quantum gravity is, instead of having a singularity, the model evolves through a bounce. And so these non-singular bounce models have become quite popular in cosmology. Many of the problems in this area are probably not problems in mathematical physics. However, I pulled out a couple that may be potentially regarded as problems in mathematical physics, or they will be. For example, once a fully consistent theory of quantum gravity is developed, there will be questions about its well-posedness, about its structure, and so on. Certainly, the question I just referred to, the singularity resolution, is a problem in mathematical physics. And there's also another problem called black hole information paradox, and this is a very popular topical problem, although I'm not entirely sure I would regard it as a problem in mathematical physics. It's this problem here. This is the qualitative description of the problem. Let me just sort of go below and discuss it a tiny bit more technically. Here's the deal. In general relativity, a black hole is formed by the gravitational collapse of a body. That is, general relativity predicts the formation of a black hole. This is a classical process. When one looks at how, after the black hole has been resolved, let's say we have has been formed, we might have a Schwarzschild solution with an event horizon. Then if you take into consideration quantum effects, quantum particle creation effects, then it turns out that these black holes emit something called Hawking radiation. That is, the event horizon is not a one-way membrane. There is some information that escapes across the horizon to infinity, and this is a quantum effect. Semi-classical arguments means we're not working with full quantum gravity, but some perturbation of general relativity with some appropriate constraints. Now, if this procedure continues, what happens is, as the radiation, which is thermal, which means it's statistical, doesn't have any information associated with it, as this information escapes, the black hole mass reduces, and eventually what will happen is the black hole will disappear. But within semi-classical arguments, semi-classical quantum gravity, there's no reason why any of the information should be lost. So what we have the situation is we have a black hole that's formed with all sorts of information. The radiation is emitted thermally, so no information is lost. And if the black hole disappears, where has the information gone? This is the so-called black hole information paradox. And it's a violation, if it does occur, it's a violation of the second law of physics, thermodynamics, and poses a problem. Now, there are various, so this is a very topical problem that interests people in theoretical physics. Suffice it to say here, I'll just mention a couple of things. There are a number of ways around it. Most importantly, either the semi-classical approach does not capture the full physical picture, and if you look at this within a full quantum gravity theory, the picture might be quite different. Secondly, perhaps instead of the black hole disappearing, it reaches a minimum mass and then explodes, and the information goes to infinity. And there are some other possibilities. So this is probably not a problem in mathematical physics, but pretty close to being so. If we had a better described theory, we could actually attempt to answer this in a mathematical fashion. In this next section, section 5, we discuss open problems in cosmology. This is actually, in a sense, somewhere between quantum mechanics, quantum theory, and general relativity. There are lots of very interesting problems in theoretical physics, and also there are some precise problems in mathematical cosmology, mathematical physics. Here's a couple of problems or topics of interest discussed a little bit, but I think it's widely taken that the biggest theoretical problem in cosmology is the existence of dark matter and dark energy. In the models, one looks at very simple models and try to find out what the predictions for observations are, and it turns out in order to match the models with observations, one has to postulate the existence of certain types of exotic matter. Dark matter, which is not seen in the sense that there's no radiation, electromagnetic radiation that is emitted that we can see, but it does act gravitationally, so we can know its presence through the dynamics of, say, for example, galaxies and so on. Dark energy is even more exotic in the sense that not only can you not see it, it has no gravitational effect. Dark matter is widely believed to be that it will be resolved with traditional physics, maybe a new particle, a change in the differential equations, an alternative theory. Dark energy is a real puzzle, and there's no really good ideas out to describe how that the dark energy problem can be resolved. This is said to be the most important problem in cosmology by Stephen Weinberg. The problem is that if there is this constant dark energy that is posited, then the only estimates of it would come from quantum gravity, in which case it would be much, much bigger than what is necessary for cosmology to solve the cosmological problems. There's another aspect of cosmology called inflation. This is the idea that in the early universe there was a period of accelerated expansion that helps resolve some of the technical problems in cosmology. The existence of inflation, that is a period in which the universe begins to accelerate, has been studied within very simple cases, but there's no proof that in general a period of inflation would take place. Now, I mentioned both of these topics, dark energy and inflation, for a particular reason. This is a little bit more explanation about the inflation problems. And that is that in both cases, a classical solution of GR, again, is going to play an important role. This is the so-called de Sitter spacetime. This is the analogue of anti-de Sitter with a positive cosmological constant. In the case of dark energy, if there's a cosmological constant acting as the dark energy, or something like a cosmological constant, then we would like the Sitter spacetime, which represents the asymptotic behavior of the spacetime, to be stable. Similarly, in the case of inflation, in the early universe, the universe undergoes a period in which it's approximately de Sitter. So again, the Sitter space, the stability of the Sitter space is important in studying models of inflation. Namely, if it's not stable, then perhaps inflation is not likely to occur, and the theoretical idea, the model, the paradigm, is not valid. So the question is what is the stability of the Sitter spacetime? Again, we have, this is based on general relativity, a set of differential equations, and problems like proving the stability of a particular equation, a particular solution, is a well-posed problem within general relativity. So some very simple results have been known for a long, long time, talking about the stability of de Sitter. So there are various theorems and results which are kind of summarized there. These theorems may apply to the case of de Sitter at late times, i.e. in models of the late universe with dark energy, but they don't necessarily apply in the early universe in the case of inflation. Namely, there isn't a theorem that says with particular initial data, generic initial data, with certain assumptions about the matter fields, that the models will necessarily accelerate. This is called the cosmic no-hair problem, and trying to prove the stability of de Sitter in the general case of inhomogeneous data is an unsolved problem. So one problem that's of importance is proving the stability of de Sitter for generic inhomogeneous data. Secondly, again, because the equations are represented by differential equations, we can have particularly rigorous conjectures in various contexts. In cosmology, what we have is it's the situation where the model is evolving with a matter distribution representing the matter in the universe. The singularity theorems tell us that in the cosmological context there's an initial singularity, that is in the past, but the singularity theorems say nothing about the nature of what the models look like as you approach this past singularity. So the next question is, what is the generic behavior of Einstein's equations as you go to the past towards the singularity? Now the Russians, BKL, have done some very good work and shown that within, well, qualitatively shown, not rigorously proven, that for general initial data, the approach to the singularity has certain features. It's vacuum dominated, that is, the matter's not dynamically important. It's local, that is, local means its behavior at different points might be different, and oscillatory. Models actually oscillate, and the dynamics are referred to as the BKL dynamics. This oscillatory nature is actually a realization of something called chaos in dynamical systems, and so the universe itself is chaotic in its dynamical behavior as you go back towards the initial singularity. Now, the BKL conjectures have been proven, have been analysed locally using qualitative methods, and there's an argument that in the spatially homogeneous case, spatially homogeneous means that there's no spatial variation, so the PDEs of GR become ODEs, and you could use various techniques such as dynamical systems to study the qualitative features of these models. They've shown that in the case of spatial homogeneity, the BKL dynamics is typical. There's an open class of open set of initial data for which this occurs. What is lacking is rigorous proofs of these conjectures and generalizations to the case of general inhomogeneous initial data. As it says here, the rigorous proofs have actually only been obtained rather recently, and they're not complete. They're not completely. It's not completely solved in the spatially homogeneous case. So one of the problems is to actually prove rigorously that the path detractor of the general spatially homogeneous models is described by the BKL dynamics, which is termed the mixed master attractor. There's a few comments about what results have been proven. And more importantly, to prove something in the inhomogeneous case, this is basically uncharted territory, prove the general behavior, dynamical behavior in the spatially inhomogeneous case, the general case of models evolving towards the past singularity. There's another problem that is of particular interest to me that I'll include in this category. That is, how do you average a tensor on a differentiable manifold? This question has not been solved. There is no covariant and gauge invariant way of averaging a tensor. Now, there's the mathematical aspect, that is, how do you define averaging, coarse graining on a differentiable manifold. There's also the application. Now, if we have a situation where we have general relativity with matter perhaps defined on an interesting scale like astrophysical scale, the matter is going to be inhomogeneous. There's going to be objects like stars, galaxies, and so on. So the matter distribution is not smooth, not spatially homogeneous. If we take those equations defined on those scales and average, we then get a coarse-grained version of Einstein's equations, which would be appropriate on large scales, in which cosmology is important. And the question is if we coarse-grain the equations, because Einstein's equations are nonlinear, when we coarse-grain the equations, Einstein's equations, to find appropriate dynamic equations on large scales, do they have any additional terms? Are there any extraneous terms that appear? And if so, what would their effect be on cosmological observations? The first part of the question is defining tensorial objects on a differentiable manifold, is certainly mathematics. The second part, to look at the interpretation of averaging, is a problem in physics.
Alan, are you there?
Yes, I am. Can you hear me?
Yes. Okay. First of all, let's thank Alan for this nice talk.
Thank you. Thank you.
Many thanks.
I think we've run a tiny bit long, haven't we? I'm happy to answer questions now, but if it suits your schedule better, I'm very happy to answer messages online or by email or whatever.
Do we have time for a question? Cristian, Roberto?
Sí. ¿Queda abierto la posibilidad de preguntas?
Sí, preguntas, por favor. Yo las puedo traducir si es necesario. Okay, so since there are no questions, I will ask a question. So this is probably a very difficult question to answer, and I would like you to have in mind undergrad students for this answer. Yeah. So what do you think? What's your personal take on the course of mathematics in the future? What do you think mathematics is going?
You mean in terms of applied math, theoretically?
Yeah, applied or pure. I would prefer pure, but yeah.
Yeah, pure is more difficult to say because the problems in applied mathematics and mathematical physics are dictated by physics. So if there's a discovery made, say, for example, in quantum gravity, everybody working in mathematical physics are going to want to work on those problems, and the physics will drive the problems. One of your colleagues, Rodolfo, was mentioning some mathematics that occurs in biological physics. Now, as biological physics becomes more and more mature and becomes more and more rigorous, there's going to be lots and lots of questions that appear within the mathematical biology context. In fact, it has already. Lots and lots of people work in various models in biology and epidemiology and so on. So to some extent in mathematics, in applied mathematics, the questions are dictated by physics. And anytime you have a system of equations that represents a model, you can do some mathematical analysis. Pure mathematics, it's harder because as indicated in my initial comments, it's a different beast in the sense that to some extent, the problems of interest are driven by people rather than circumstances. And it's typically driven by people that are regarded highly and their opinions count highly. So problems that are historically difficult, haven't been solved, problems posed by famous mathematicians now. And that is a little harder to predict where that's going to go. Only to say that if a mathematician is a good mathematician, regardless of whether it's pure or applied, if a pure mathematician hears of a problem in applied mathematics that's interesting, they're going to work in it. And you'll see lots of examples of contributions being made to mathematical physics by pure mathematicians, and vice versa. So in a sense, there's a little bit more interplay than perhaps I've indicated. But the motivation for pure mathematics is much more difficult to gauge. I don't know what it's like in Chile, but in Canada, the Mathematical Society, each grouping, each field has its own opinions on what is the most important mathematics, and it becomes quite idiosyncratic. There's very little common ground between the various groups in pure mathematics within Canada. So it's an interesting question. I think as professors for the students, I mean, the students should be asking you, what do you think should be on that list? Because the list is incomplete, and you know, some of the questions that you might find interesting might be interesting within your programs or so on, that the students would benefit from some more local knowledge, if you will.
Okay, thank you so much.
You're welcome.
So any final comments or something to say before we thank again Alan? Okay, Alan, thank you very much for your nice talk.
Thank you very much. Thank you for inviting me.
Very much.
Thank you.
Thank you.
Bye, everyone.
Thank you.
Bye-bye.
Bye.